In this video, we'll review the trigonometry which is associated to each right triangle. Recall that if I have a right triangle, that means there is a single 90-degree angle in the triangle. That opposite that 90-degree angle is a side of the triangle that we call the hypotenuse. If you then pick any of the other angles in the triangle, I'm going to pick this one on the lower left and I'll call it theta. Associated with theta are two other sides of the triangle, and they have names relative to the chosen angle theta. The side next to it, forming the angle with the hypotenuse, is called the adjacent side, and the side opposite of it is called, well, of course, the opposite side. That's the angle opposing theta. Once we've decided what the sides are of our triangle relative to our angle, we can form various ratios of those sides, those three sides, and those ratios have the common names, and they determine the three famous trigonometric functions that we call sine of theta, cosine of theta, and tangent of theta. These are how they are defined in terms of right triangles. Sine of theta is defined to be the opposite over the hypotenuse, so you measure the opposite length here and the hypotenuse, and you take that ratio of lengths and you get a number that we call the sine of the angle. The cosine of the angle is the adjacent over the hypotenuse. And then finally, the tangent of the angle is the opposite over the adjacent. Let's investigate these in an example. So suppose I have a triangle and I've got a right triangle, of course, 90 degrees here. Opposite to that is the hypotenuse, and I've measured it to be 5 inches long. I've then picked one of the angles, this one here that I've called theta, and I found that the side adjacent to it is measured to be 4 inches. Using that information, I want to find the three trigonometric function values of theta. Of course, to do so, I'm going to need to know this missing side here. And we don't have to measure that, although we could. We can use the Pythagorean theorem to figure out that missing opposite side relative to theta. And recall that says that if I look at the sum of the squares of the sides or the legs of this triangle here, I should get the square of the hypotenuse. So 4 squared, which is the adjacent side, plus the square of the opposite side, which I do not know, must be equal to the square of the hypotenuse. If I calculate that, I get 16 plus the square of the side that I'm looking for is equal to 25. Now subtract over. The opposite side squared is 25 minus 16, which is 9. Notice that this is the square of the length that I'm looking for, so I'm going to conclude then that the opposite side must be plus or minus the square root of 9, or plus or minus 3. But of course, these are lengths that we're talking about, so we'll take the positive square root of 9 in order to find that the opposite side is in fact 3 inches long. Now that we've found all three sides of the triangle and we have a perspective of what is the opposite, adjacent, and the hypotenuse, we can easily form these three ratios for this angle theta. So in fact, the sine of the angle is the opposite over the hypotenuse, that's 3 over 5. And then the cosine is the adjacent over the hypotenuse, 4 over 5. And finally, tangent is the opposite over adjacent, 3 over 4. Notice that these expressions here have no units attached to them. They are ratios of lengths and therefore are dimensionless quantities in themselves. This is typically used in applied problems. We take advantage of the fact that things like calculators can estimate the values of these trigonometric functions for us accurately and conveniently, are accessible on our calculators, and we can use that to solve applied problems like these famous problems such as this one, where I'm going to take a flagpole and try to measure the height of this flagpole here. So here's a flag on a pole. I want to find how tall it is by using some measurements on the ground which are accessible to us. So here's what I'm going to do. I'm going to stand 15 feet away from the base of the flagpole, and then using an instrument on the ground that I can use to kind of look up and measure that angle of elevation to the top of the flagpole, I found out that that angle of elevation is 40 degrees. So I want to find the height of this flagpole here, and I'm going to use trigonometry to do that. So I look at the sides that I am interested in and the sides of my triangle that I have. I have this adjacent side, that's 15 feet known to me. I want that opposite side, that's the height. Therefore, I'm going to use a ratio that uses those two sides, and the right one for us is tangent because it uses opposite over adjacent. So I'm going to set up the ratio, the trigonometric function. It's tangent of 40 degrees is opposite, which is the height we're looking for, over adjacent, which is 15 feet. Solving for the height is the tangent of 40 degrees times that 15 feet when I bring the 15 feet over. I can then go to a calculator and make sure that you're in degree mode when you do this. So you have to set your calculator into the appropriate mode. We're using degrees in this applied problem. And I take tangent of 40 degrees and I find it to be about 0.84 for the tangent of 80 degrees. That's a rough estimate there. And I take that much of 15 degrees. Remember, this has no units attached to the tangent. The 15 feet was a length, so it has units attached, and so this tangent of 40 degrees is essentially some sort of scaling factor. We're going to take 84% of 15 feet to get about 12.6 feet, and so the flagpole is about 12.6 feet tall.